about InfluxDB. This is our Twitter handle. Say nice things about us online. So who here has heard of InfluxDB before? That's good. Anyone using it? You are? That's good.
We know our question, right?
I don't know. We'll see. All right, so not knowing exactly what the crowd is going to be, I'm going to go through a quick intro of the subject in general. So first, let's forget about the words database and distributed and scalable. And let's just start with the words time series. And I say that because even when I tell some of my techie friends that we're writing a time series database, I get this kind of look from them. But it's pretty simple. It's just it's values with timestamps. It's just date and time and the values that go along with when the values we're collecting. So that could be anything from CPU usage taken every few seconds or at whatever regular interval. It could be cumulative steps taken from a fitness tracking device. Happy InfluxDB users. So those are all individual time series. And if you collect a bunch of those things together and put them in a database, you got a time series database. So let's talk about actual types of data that are being put into time series databases. Metrics is a very common one, and a lot of you here working in data centers. This would be a very common type of data you'd want to put in a time series database. Time series is stock trade, stock prices over time, stuff that the financial world would be interested in. User analytics and real-time business intelligence. Event data. So this is an Apache log. You could break this up into a lot of individual time series if you wanted, like the number of 200s per minute or errors per minute or anything like that. And I know this type of data you might be thinking, well, use Logstash or something else to pick apart a log. And that would probably be the case, but I guess the bigger point here is that it could be the types of data could be regular data collected at regular intervals, or it could be irregular intervals, event-driven stuff, user clicks, and that sort of thing. So let's talk about some of the use cases for it. So DevOps is probably one of the biggest. I mean, of the current users that we have, people collecting metrics from servers is probably the most common right now. Again, analytics, business intelligence, and sensor data and IoT. This is another area that we're targeting. Both on the industrial and on the consumer side. So, on the industrial, it could be things like monitoring factory production lines. It could be power generation. On the consumer side, it would be things like fitness trackers, smart home devices. And this is just a quick point I keep in mind when you're thinking about time series data. It can come from the measurements that you're taking can come from both physical or logical devices. It could be a thermometer, or it could be some sort of logical sensor in your software and application. All right, so we know what type of data we're dealing with. Now let's talk about storing it. This is usually the first question we get when we tell people we're writing a time series database. Why not just stick it in a regular database, Postgres, and order by time, right? We'll be able to do this forever. The problem with that is it doesn't scale very well when you're collecting enough of it. So, a short example of that from the metrics use case. If you have 10 hosts, very small number of hosts, 100 measurements per host, which is also a fairly small number, collected every 10 seconds, 365 days a year. You've got 3.1 billion records. So that's used to be quite a large Postgres, but that adds complexity. It can be done. We're not denying that. We know it can be done, but we just felt like there was an easier way. So next, kind of the next thought is well, maybe we'll just keep the summaries of the data. Maybe we don't have to have every 10 seconds. So if you collect 1 hour averages, you're down to 8.7 million records per year. It's a lot better, certainly manageable. But you've lost a lot of detail. You've lost ad hoc variability. You're kind of looking at a blurry, low-res image of what the actual data was, or the data that you might like to have collected and stored. So then the next question we usually get is, or the next thought is usually, let's use something like Cassandra or HBase or something that's already distributed. But the problem with that is that there's still too much application complexity. And this is actually how Influx got started. If you're not familiar with the story, Paul Dix and Todd Pearson, the founders of the company, wrote a couple of time series-like databases on top of Cassandra on 2 different occasions. And going through that, they realized that the world could use an easy-to-use open-source time series database. And we'll go through some of the troubles that they ran into leading up to that. So they had to write application-level logic and scripts to compute. In summary, Cassandra didn't have that built into it. And then a tougher problem was application-level balancing. Even though Cassandra is a distributed database, they found that in time series use case that they actually had to write application-level code still to handle the balancing of the code. And you can kind of see this if you look at the other time series databases that are out there. Influx is not the only one. It's not even the only open source one, but we'll look at some numbers in a little bit, in a few slides later. Data locality for queries. So with Cassandra, you end up moving larger amounts of data across the network. And what you'd really rather do is move your code to where the data lives and do as much work as you possibly can there, and then roll that out, and then ship that answer to the code to the user. And then how do you handle retention? With time series data, you're usually dealing with high precision data that you want to keep for a limited amount of time. Maybe a week or a month. This is not necessarily long-lived data, or at least not in its full resolution. You want to aggregate into a medium or lower precision, and maybe eventually trim that data completely or store it in a indefinite retention policy. So this, and with this issue, that also means that you're doing almost as many deletes as you are writes. And a lot of databases don't handle that very well. So on top of that, there's even more stuff. I mean, if you build a database on top of Cassandra, you get those things working, then you're probably still going to need to write some web services. I mean, the whole reason you're doing this is probably for monitoring or have a dashboard, some sort of metrics, dashboard display of your data. So you're probably going to end up writing web services on top of it to make that possible. And then you're probably going to end up writing libraries to talk to your web services, libraries in your favorite language. And then you're going to end up writing code to collect the data. And you're going to write more code to visualize the data. So to kind of summarize, there are 8 open source time series databases listed in Wikipedia. Actually 9, I think, if you count Influx. Of those, 6 of them are built on top of Cassandra and HBase. give you an idea of, those folks thought we'll build it on top of a distributed database, and it was enough work that they actually ended up open sourcing it and making it available. It's a lot of extra work. There were two that were no longer maintained. I'm not sure what they used as an underlying technology. I didn't really dig into them. And there are none built on top of SQL that I could find. So this was kind of the, something that Paul said, our CEO. Building an application for analytics is like building a web app back in 1998. You spend most of your time working on infrastructure before you actually get to work on the things we're really all excited about building to begin with. And it really shouldn't be that. If you've got some idea for something you want to do, you don't want to spend months, creating infrastructure, whether that's writing your own thing on top of Cassandra or maybe a lot less time, but still significant work in figuring out how to deploy these things on, the frameworks for it. So enter InfluxDB into the picture. Obviously, time series database.
Can you please check your microphone if it's muted?
Well, yeah, maybe.
Hello? Testing? Oh, so I've been on mute the whole time. You guys want me to start over? All right. On the back? Oh, okay. All right, so no external dependencies. No shared libraries, no third-party software to install, no other databases underneath, anything like that. It's all rolled into one. Distributed and scalable, easy to use and install, maintain, and we're going to go through. We'll see this in a little bit. We'll demo and install so we can see just how hard it is. We've all heard that story before, that from the sales guy, that it's really easy to install and use, and then you get it home and it's actually quite a bit of trouble. Open source, of course, or I wouldn't be here. But it's MIT licensed, and it's written in Go. If anybody's a talk for another time, but another great language from Google, open source as well. So let's look at the data model. So at the top, and this isn't really part of the data model, but I put it in here just so we can show how it all works. You've got the Influx daemon that manages everything. You've got one of these running on each node, whether you've got one node or lots of nodes. And it can manage one or more databases. And then inside of each database, we have measurements. And those are the things that we looked at kind of like before, CPU loads, amount of memory used, disk usage, could be anything you want to measure. Temperatures. And then we have tags. This is metadata. This tells you the things that where the things you're storing came from, or any kind of information about it. And something important to note is that in Influx, measurements and tags are all indexed. So any search on a measurement or a tag value, those searches are all very quick or cheap. And then we have a series. Hence the time series, which in Influx, a series means a measurement plus a unique tag set. So in this example, we have, I think there's a pointer on here. I don't know where it is. Anyway, so we're collecting CPU measurements from Germany in the Western region. Or we could be collecting CPU measurements from Germany in the Eastern region. So either one of those little streams of data would be a unique time series. Then inside of a series, we have points. And the points are just the values, the actual data values themselves, with their timestamps. Now the example, the little table data over there shows just one value column. And that's common in time series, just to have one, a timestamp and a single value, like CPU measurement. We do support multiple fields. Off the top of my head, I can't think of a use case that I know of that anybody's actually using in the field. I'm sure there are, but it could be maybe if you're storing event like mouse event clicks, you could store X and Y coordinate of where the click occurred. But more typically, we just see this, a single value. So how many of these time series can the database handle? The answer right now is I don't know, but the goal for the upcoming version 09 release is 1.2 million value or points per second written across 1.2 million series. So I know for a fact that we can handle 1.2 million series. My laptop will easily do that, no problem. We're not there yet on the number of points per second. We're somewhere around 450K. We're mostly concentrating on getting features up to a certain base level, and then we'll hit the low-hanging fruit on performance, and I think we'll pretty easily get up to the 1.2 million points per minute goal. So let's talk about data retention and replication. So these are a couple of the problems that we talked about that, if you're building on top of an existing distributed database that you're going to have to deal with yourself. As the data ages out, you want to downsample it, store it in a lower resolution, longer term storage, or age it out completely. In InfluxDB, we have what are called retention policies. And this makes managing retention very easy. When you write data, it's always written to a retention policy. And when you create a database, every database has to have a default retention policy. If you don't, it'll create one for you by default. And if you just write data in and you don't specify a particular one, it gets written into the default. And the default maintains or retains data indefinitely. So you want to be careful. You don't want to throw that into production and just start beaming tons of data at it, because it's never going to go away. You're going to quickly probably overflow your disks. You can create as many retention policies as you want. And a retention policy is it's a duration, and we'll talk about in a second, is a replication factor. We also handle replication through retention policies. So you tell it, create a retention policy that's 1 hour in duration on database foo, and its replication factor is, if I'm running on my laptop, my replication factor is going to be 1 because I'm not replicating it anywhere. But if you're running on a 3-node cluster, maybe you set your replication to 3. And so that seems like a really short discussion of it, but it's about that simple. And I'll show you how you create a retention policy, and once you write data into it, that's it. The database handles in the background cleaning up. So continuous queries. These are used for downsampling or aggregating data on the fly. So you can create if you have a high-res stream of CPU measurements coming in, on your dashboard, you want to look at the averages, over a period of time. You can create a continuous query that will, that could be an expensive query, maybe not, depending on what exactly you're computing. But you can create a continuous query. It'll create the roll-up or the aggregation on the fly for you in the background. And so that does a couple of things. One is it's doing it on the fly. The other is that for expensive operations, they get done periodically, and then everybody just grabs that result. So it doesn't get recomputed over and over. Stored in the database. Once you create them, they live there and run on their own. So I'm covering most of it without hitting the clicker here. All right, so let's talk about actually writing data into the database. We use HTTP as a transport for writing it in. You can just see you just hit the write endpoint and give it some data in the -d param there if you were using curl to post it. We currently use JSON as our format. You can see, let's see, how do I get a, you can see up at the top, you tell it what database you're writing into. Here we're writing into a retention policy name default. Probably not the best choice of names for the for my slide here, but if you create a database, it actually creates a policy name to default. So even if we didn't specify that here, it would have still written into the one name default, or whatever the policy was set as the default for the database. But then we have a list of points. The name there you see CPU load short is what we were looking at called the measurement. So that would be steps taken, CPU load, temperature, whatever the thing is that you're measuring. And then the tags for where the data came from, timestamp, and then the field values. It's mostly schemaless, except that once you write in a field value, it takes the type from it the first time, and then it expects to always get, for that field, that type of data. So querying data, we have a query endpoint, and you pass in a Q param with the query that you want to run. And the language itself is SQL-like. We didn't try to stick to any particular SQL language standard. We just borrowed very heavily from it, and in places where it didn't make sense in the time series world, we adapted it to fit. So here's an example query. If you've never seen Influx before, but you've worked on SQL, this probably still looks pretty familiar. We're just selecting value from CPU load short, where a tag equals some value. And then we get back a result in JSON format. You could get back one or more series in a result. In this case, we've just got one series. And so, as far as just writing data in and getting it out, again, it's just that simple. Something I was hoping to show, but I don't, is some visual dashboards. But we've been going through, anybody that keeps up with a project knows that 090 has been a major change from 08. Basically a rewrite from scratch. There's probably 4 or 5 lines of the old code left, I don't know. But so Grafana definitely works with 08, and it will work very soon with 09. I couldn't get it to work for the demo. Not well enough that I felt comfortable getting up in front of people with anyway. But it'll be working again soon. And so anyway, Grafana, if you haven't used it, is a really nice third-party graph or visual and dashboard application that works with Influx. It knows how to talk to Influx and show you what's in the data and allow you to create visualizations of it. All right, so now this is going to be the unscripted part of this thing, of the demo here, or the talk. We're going to actually go through an install, we'll look at config, and we'll see how you would, we'll write data to the database, discover, and query the data. All right. Can everyone see this okay? You guys in the back read that, or do I need to make the font bigger? Good? Okay, so what I've got here is, I'm going to run this, I'm going to fire up a Docker real quick, and just to show you what's in this Docker. We're going to just pull a basic Ubuntu image, and we're going to add in that deb install package which I built. You can do a wget off of our website to grab the the latest release candidate for '09. And then after you do that wget, the process would be just like what you're seeing here. You basically wget it and you run it. That's it. So let's see that happen. I'm probably going to have to get some expert here to tell me the right. Oops. So I'm going to export a couple of ports here that Influx uses. 8086 for the data interface, and then port 8083 for the admin interface. The admin interface is kind of an optional thing, but we'll take a look at it. Let's see if we can make this bigger too. All right, so we're in. We have our deb install package there, so we'll run that. All right, so no going to get coffee while Influx installs is done. If we go look at the directory to see what we actually put there, so you can see the thing at the top is a command line interface. Then there's the daemon and a couple, the init script. So there's not much there. I mean, truly no external dependencies on anything else. So let's fire it up. I mean, we could at this point we could start it through your normal, whatever you're managing daemons with, but we'll run it from the command line here. So I've just launched it with actually with no configuration file at all. When you run it from the command line like this, it just ran with an internal default config. Obviously, you wouldn't install it and run it in production this way, probably. But as far as experimenting with it, seeing if you like it, getting up to speed, doing a lot of development work against it, this works great. Oops. So that guy's running. So let's, I've got a little app that will, actually before we do this, let me bring up something else. So if we go to the admin port 8083 that we exported, you'll come to this. This is just a real quick little admin app that you can, or admin interface that you can use to play around with it. We'll connect. Right now we have no databases, which is not a surprise. We just installed it. If we want to create a new database, tell it, so we've created a database now. If we go explore data in that database, obviously we haven't done anything yet, so we have no data to explore. So what I'm going to do now is I've got a little app that I wrote that uses our library, our Go library, to interface with it. We have a number of different language libraries, bindings out there. We have Go, of course. We have Java, Ruby, Python. There's a bunch more. There's probably twice that many more out there that I'm forgetting about. Some of those will probably need some work to come up to speed for '09, but they will. So I'm going to run this little test app that's just going to put some data in there. I don't remember what I named it. So it's just ticking off data into the database, 5,000 points at a time. It says there at the top, 3,200 series that we're writing. All right, so I've got that thing putting data in there for us to play with. Open up another tab here, and this time we'll go in and look at it. Actually, we'll go back through the web interface here. And now if we rerun our show measurements, now you can see we have some measurements to look at. I'll show you this also. There's some basic diagnostics that you can run just to see what's going on with the database. Let's go back to our measurements. All right, so we see these things that we're collecting. So maybe we want to, one of the big things, like I was talking about with Grafana, is data discovery. When you've got a million series and thousands of tags or thousands of possible tag values, just knowing what's even out there to look at is a problem in itself. And then there's also the possibility that there are gaps in time. You may be collecting CPU data for this window of time, but maybe not for this window of time. So if you go to query it, maybe there's nothing there at that particular period. So one of the things is discovering what's available for this window of time that you're interested in. If some anomaly happened at 4 o'clock yesterday, you first need to go see what data do you have from 4 o'clock yesterday. And that can also come into play if you're collecting metrics from VMs or Docker images that are running. Those things are, they come and go. So we know we're collecting these measurements. Let's see what we know about these measurements. We can say show tag, show tags from CPU. Oh. No, show. Oh, I'm forgetting my own language now. What's the error? Found tags, expected continuous database. No, it would be show. Tag keys. There we go. So we can see that we're collecting tag keys from with the name country, data center, region, and server. And so then we would wonder what values are we collecting in those individual tags. So we can say show tag values from CPU with key equal. Good, I got that one right at least. Okay, so we can see we're collecting CPU measurements for these countries. And there were some other things, other key or other tag keys there. We could also, if you wanted to query for multiple keys at the same time, you could say country, region, server, I think was the other. So then it'll spit out a list of all the different, for the country tag, we're collecting these things. For the data center, we're collecting these. For regions, and then servers. All right, so I'm going to, just to show it, I'm going to switch over to the command line interface. So we're connected to it. And let's actually query some data. So Now we're writing data in, kind of fast. I'm not super fast, so we don't want to select from a huge range of time, or we'll be watching data scroll by for the rest of the presentation. So let's say time is greater than now minus 1 second. So it just spit out, a ton of values. We could count the values that we spit out. Maybe with CPU measurement, that might be more interesting to look at. And then we can, limit our search by the tags, of course. And we can so that's for the last second. Let's see. We might be interested in, let's see, for the last 30 seconds. So we just asked for the CPU measurement, the average CPU measurement for the last minute, grouped in, or the last 30 seconds rather, I think, grouped in blocks of 10 seconds. And you can see there with the results that come back, we get back the name of the measurement, and we get back the unique tag sets from which that data came. Another really useful feature in time series is being able to use regular expressions in your queries. Let's say, for instance, can everyone still see at the bottom of the screen? Let's see. And we know that we have servers that end in 000 something, and maybe we only want to see the values from odd-numbered servers or something crazy. Obviously not a good real-world use case, but just to show the feature here, we can say where server. And then we have a regular expression operator. You can see the equals and then the tilde. And we write regular expressions this way. So we wanted odd numbers at the end of the line, so 1, 3, 5, 7, and 9. Ah, what did I do? Oh, thank you. And maybe here we have, it's possible we have no values. Oh, there we go. So there you can see we're only selecting from odd-numbered servers. You can use regular expressions in, querying in the where clause, or you can use them in the from clause also. If you wanted, the data that I've got here is not great for it. We could, select from. Let's see, let me make this. we could say, let's see. Again, this isn't great data for this example, but we could say T or RX, and select from series names or from measurement names that way. Let's see. So that's all the examples I can think of off the top of my head. I mean, there's a lot more to it, more than we have time to go through today. But let's take a quick look at the configuration file. I don't think I have Vim installed on here. Let's see. Oh, actually, I dropped out of the. It's not the window I want anyway. So it does, when we were running, we started it up from the command line, and so to run that way, I didn't explicitly tell it to go use the config file, so it just ran from the config, it's in memory or built-in default config. Had we actually launched the service, it would run basically the same config, installed in, at least on the Ubuntu system and in the normal config directory. So we have, pretty simple, basically just stuff you would expect to be able to set, addresses to bind to. You can set the ports where the data comes in. We do report anonymous usage statistics but you can shut that off. Basically, that's just we're just trying to get an idea of how many people are actually installing and running it. Then there's some configuration options for join URLs. If you're gonna run it in a cluster, you would set up. I don't have enough time to go into setting up a cluster, but we have broker nodes and data nodes. Typically, you'll have a small number of brokers and a larger number of data nodes. Kind of as the name implies, the data nodes is where the data lives. And that's where the writes end up going into. You could see that we didn't do any sort of authentication while we were doing queries. That by default it comes up with it disabled, but you can enable authentication, create users, set passwords, and that kind of thing. Then there's the admin interface, config settings. That was how we got to the little web page that's embedded in it. Graphite. So we have some plug-in support for like Graphite, CollectD, OpenTSDB, and there's more coming. We're working on. We're just starting to work on more collection. Some config settings for broker nodes, data nodes, logging, snapshotting, and that's it. I mean, there's really not a lot to it. You install it, come in, tweak some config settings. There's documentation on the website. Please, if you're interested in playing around with it, go through the config file, go through the docs. If there's anything missing, let us know, or if anything confusing that we could do better in the docs. And of course, it's open source. So we welcome PRs. We have it's a pretty active project. It's been open source development's been going for just over 2 years now. We've had about 5,000 commits and about 100 contributors, a little over 100 contributors. So it's a pretty active project, and we do, we're very friendly. We're not you're not going to get any ranting Torvalds emails back from us. We really do welcome and encourage everybody to help us out. So that's all I'll cover for demo, unless anybody has any specific questions about query language or anything while we're in here. Okay. So thank you. That's it. And we do have a few minutes if anybody has questions in general about Influx.
You said clustering on the documentation says don't use it at the moment. What's the current status?
I think if you go, actually, so that's a really good question. If you just hit InfluxDB's website and click on the document link, it takes you to the 08 documentation. Yeah, and you'll see that up in the URL. It'll say 0.8 up there. And the clustering there was definitely not production level. We're getting pretty close with 09. The release hasn't come out yet, but we've got one of our larger users that we work with on a daily basis, and we're getting the clustering stabilized. So that should be pretty soon. You can go in. There may be a better way to get to it, but I always just click on the docs link and then change the 08 to an 09 if you want to get to the 09 documentation. I'm sure there's a better way. Right. What's that?
You get access denied when you do that.
Oh, really?
Yeah.
Okay, bad advice. I'll see you after the talk then. We'll figure it out. Another one? So the question is, I'm sorry? Yes. So the question is do we have any write buffering going on? Was there more to it, or was that? There's no buffering going on. So, and we encourage, and maybe I don't fully understand the question, but if for performance, we encourage you to batch the writes up and send many points in a single write. The performance will be, or the throughput would be much higher if you're writing 1,000 or 5,000 points at a time, as opposed to writing single values at a time. Does that answer your question or no? Oh, no. Writes can come in through any node, and then it will figure out where the write needs to be routed to. So as as part of the scaling, the performance numbers that I was talking about earlier, 1.2 million points per minute, is with a single node, and then we expect that to scale hopefully linearly with nodes as close as we can get. So we'd like to have 10 nodes writing 12 million points per minute. More questions? Yeah. Okay, so the question is, could I give an example of how the retention policies work? Let me, real quick, well, I probably don't have time to do it. Basically, you would go in and say, let's say that you had CPU readings collected every 10 seconds, and you wanted to create and you're only holding that for, a week, those readings, because you're collecting them so fast. But let's say for longer term, you wanted to move that into like longer term retention policy. You could say, go into the query language, on the command line and say, create retention policy, CPU, 6 months. You give it a name like that, CPU 6 months, on database foo, duration equal 6 months. 6M would be 6 or 6 capital, whatever it is. I've forgotten the units for it there. And and a replication factor, and that's it. So you give it that one command, and now you've created a retention policy named CPU 6 months. And so you can select from your higher precision into that one, or you could write a continuous query that automatically downsamples the data into it, like you compute the mean, or the average of the CPUs for that period of time into the longer retention policy. And I don't know if that answers your question. Under the covers, a retention policy, the shards actually belong to the retention policy. So when the collector in the background is going around every now and then cleaning up retention, data retention, it looks at the retention policy and says, okay, this retention policy is up for collection. What shards does it own? And then it goes out and cleans up those. That data is old, so it cleans them up. Does that? It depends. Yes. No, you don't have to do that. More questions? How are we doing? We got a few more minutes.
Do we have any further questions?
The question is there a way to export the data? Off the top of my head, I don't know. In what type of format? Like? Not yet. And I don't. There's nothing in the immediate plans for that I know of. You can. Is the next question you're going to ask me how that works? No? You can. I actually don't know if that works yet, though. You can do it, though. Yeah. Yes. But the answer is yes. That is definitely going to work. Yeah, I hope that works in 09. Any more? So the question is, are all the inputs for data the same speed? The answer in 08 was definitely not. The reason being that collectd, for instance, came through a custom interface that skipped over the JSON deserialization. In 09, I'm not sure. I didn't personally make that change, and I haven't looked at the collectd. The collectd was a contribution from the open source community in 08. One of our guys, I think, went in and made it work in 09 also. But I know that would have taken probably a significant amount of work. When he did it, I don't know if he changed it to go through the JSON interface, and if he did, then the speed is going to be about the same. If he left it as a binary interface in some way, then it's still going to be much faster. I know from profiling the database that we spend on, at least on my laptop and on kind of typical hardware, about 50% of the processing power right now is spent deserializing JSON. So that's low-hanging fruit. I mean, the good news is that's that's like this big glaring, or big shiny piece of low-hanging fruit for performance for us. And we know that we've got a number of ideas about how to make it go quicker. So. Well, I'm not right. I mean, from a performance point of view, binary is quicker. I'm not sure if it supports a binary interface in 09. It depends on how that conversion was done. A couple more minutes. Anybody else?
Maybe I have one last question.
Sure.
When using Graphite Web, we have a lot of mathematical functions we can use to transform our data points. Does InfluxDB provide something like that?
I'm glad you asked that question. And I don't know all the functions that Graphite provides, but there are, we have things like, derivative, and I don't think derivative is implemented yet, but I think it will be by 09. And derivatives and percentiles and sums and means and many statistical. Is that what you're asking? Those type of functions?
Exactly.
Yes. Yes. And when we rewrote it for 09, one of the problems in 08 was with the architecture of it. It was fairly difficult to add some of those things. We struggled. Anybody that used 08 a lot knows that we struggled a lot with derivatives, trying to get that to work right. Some people wanted derivative of, from this point to the last point, and some people wanted derivative from the first point in this bucket and the last point of the previous bucket. Some people wanted the derivative from the first point in the bucket to the end of the bucket. When you're grouping by time. So the old engine didn't handle that. It was not easy to write that code in the old engine. The new engine handles this much better. So I think the number of functions that we support will grow pretty quickly as once we get 09 out. So the question is, when will 09 be released? Today is April 22nd. I think the goal is to have it out at the end of April. So I have to check with home base and see how the guys have done the last few days since I left. It's an aggressive goal, the end of April, but we are getting close. Our main thing is trying to get clustering stabilized and distributed queries. That was another topic I didn't cover. Yeah.
Okay.
I think that's it. Thank you. I appreciate everybody coming.
That was David Norton.